got some rather lovely friends, Dominic.
No way. You should check out our asking place.
Oh yeah, I should really ask for a sign.
Stay away from Cathy.
Oh, okay.
Oh my god, what are you doing?
So sorry. Do you want my house is nearby. Could you grab some towels?
Okay, sure, that sounds good.
So, what's a series like you doing in a domain like this?
I don't know. I think I'm just looking for someone.
Someone romantic?
I don't think there's anyone with a series that is right for me anymore.
Oh, really?
What's your series?
Here we go. Oh, that's a beautiful series.
Thanks. Well, let's see what we're together. I guess this is our series together.
Ah, you don't suppose that it, might converge or something like that?
Let's do my little special test and see. So, my special test is if the series sum of infinity of an is convergent, then the limit of its sequences must go to 0. Let's start. First, let's let a series of n equal to a1 plus a2 and so on until an. Then that means any of the sequences in the series must equal to the series n, taking away its predecessor of Sn minus 1. By the clause that the sequence must be convergent if the series is convergent, it makes sense since if the sequence is divergent, then the series would grow much bigger. Let's let the limit of n go to infinity Sn equal to s. Since we know that as n minus 1 approaches infinity, as n approaches infinity, the limit of n goes to infinity as n minus 1 is also equal to s, as before. So now we have this limit of n approaches infinity, Sn minus Sn minus 1, which can also be written as limit of Sn minus limit of n goes to infinity, Sn minus 1. As we can see from before, an is equal to Sn minus Sn minus 1. This whole thing would equal to limit of n approaches infinity, an. By the fact that we know Sn and Sn minus 1 both approach s, s minus s is equal to 0. Therefore, the sequences must approach to 0 if we want the series to be convergent. Oh, it looks like the sequences do converge in our series, but it doesn't really say if we definitely converge or not.
That one looks like an old convergent series that I used to know. Yes.
Yeah, I think you're right. They do look kind of similar.
Yeah. I do know a test, the limit comparison test, and that one can show if two series converge or diverge together.
Huh, really?
Here, let's have a look.
So we have the series an over the series bn as n tends towards infinity, and that can be equal to c. Now we can squeeze this value between the values of little m and big M, and then manipulate this to get m bn is less than an is less than big M bn. Now, if bn is convergent, if the series bn is convergent, then the series of mbn is going to have to be convergent as well, because no matter what the coefficient m is, it cannot affect the convergence of the series. Similarly, if the series bn is divergent, then the series little m bn is also going to have to be divergent, because no matter what, again, the coefficient is, it cannot affect the divergence of the situation. Because the series an is caught between these two, in all situations, we can show that the series of bn and the series of an either converge or diverge together.
And the limit is equal to 1.
But that's not possible. I didn't. There can't be anyone. Wait. Do I know you? Are you that guy from?
You're that girl who ran into me.
Glad I see you again.
Yeah.
Especially not here.
Wow. I've actually got some friends going for dinner tonight, and we converge and all. Would you like to go?
Sure. Let's give this thing a try.
Hey Dominic, thanks for your shirt. No problem. No, I wish I could take you to the limits, so maybe we could test out convergence.
Really?
Yeah, I have my series right here.
Let's see. Oh wow, I have mine too. Look. Huh.
Do you think we should test for our convergence?
I don't know. I guess it's worth a try.
The comparison test. Suppose that we have two series, the sum of an and the sum of bn, and these series are series with positive terms. The first part of the comparison test states that if the sum of bn is convergent, and that the terms an is less than or equal to bn for all n, and the sum of an is also convergent. Part 2 states that if the sum of bn is divergent, and that the terms an is greater than or equal to bn for all terms n, then the sum of an is also divergent. To prove the comparison test, let's set up some new variables. Let Sn equal the nth sum of the terms ai, Tn equal to the nth sum of the terms bi, and T equal to the infinite sum of the terms Bn. Since the series Sn and Tn may only have positive terms as stated by the condition for the comparison test, the sequences of the partial sums of Sn and Tn are only increasing. Also, the series of Tn approaches the series T as n approaches infinity. So, Tn is less than or equal to T for all n. Since ai is less than or equal to bi as stated by part 1 of the comparison test, we have Sn is less than or equal to Tn. Therefore, Sn is less than or equal to T. Since T converges and it is monotonically increasing, it must be bounded above. This means that the sequences of partial sums of Sn is increasing and bounded above. The sequence of the partial sums of Sn is convergent by the monotonic sequence theorem, and Sn is equal to the nth sum of the terms ai. Therefore, as n approaches infinity, the sum of an is also convergent. Now, for the second part of the comparison test, we have to assume that the sum of bn is divergent. Therefore, then Tn approaches infinity as n approaches infinity, but however, ai is greater than or equal to bi, so Sn is greater than or equal to Tn. Thus, Sn approaches infinity, therefore an diverges.
You gotta use my test. This is the ratio test. So for any series of that form shown, if we take the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term, and we call that limit L, if L is less than 1, the series is absolutely convergent. If L is greater than 1 or is infinity, the series is divergent. And if L is equal to 1, it's inconclusive. As we all know though, everything needs a proof. Now, we'll look at the first case. And for the third case, where it's inconclusive, we will prove it by contradiction. Now, we see here a p-series with p equals 2, so it's n squared. If we crank the handle, we see that the limit is 1. But by the p-series test, we know it's convergent. If we look at the second case, we have p equals 1. We crank the handle yet again, we'll find that the limit is again 1. But by the p-series test, we know it's divergent. Therefore, when the limit is 1, we don't know if it's divergent or convergent. Oh no, it doesn't work. Oh yeah, the ratio test is inconclusive sometimes. Should've listened to my math teacher at that point.
Oh no, don't worry about it. We can try my test, right? Okay. Well, I actually worked it out here, and it turns out that our series is greater than 1 over n, which is a divergent series. So I guess that means